Now the next one is metallic solids. We had dealt with ionic solids and molecular solids. So now what is metallic solid? In case of metallic solids, the constituent particles are metal atoms. What do you mean metal atoms? See, now you take sodium itself. Its atomic number is 11. Its electronic configuration is neon 3s1. So the inner electrons along with the nucleus, we call it as kernel. And this is what the valence electron. So this is considered, the kernel is considered to have positive charge and the valence electron is considered to be what charge? Negative charge. So how will you represent this metal atoms? The kernel, then the valence electron. Kernel, valence electron. So the constituent particles you can write as metal atoms or kernels in a sea of delocalized electrons. Sea of delocalized electrons. Kernels in a sea of delocalized electrons or positive charge in a sea of delocalized electrons. Why? This positive charge or the kernels, they are fixed. Only the electrons are able to what? Move. So we call it as kernels in a sea of delocalized electrons. The electrons only will move and the kernels are fixed. So this is how it is. Got it? So what happens? In case of metallic solids also, it's an interaction between what? Positive charge and negative charge. That is, the kernel is having positive charge and the electrons are having what? Negative charge. And that interaction is known as what? Metallic bond. It is known as metallic bond. So the interparticle force in case of metallic solids is what? Metallic bond. So it's the interaction between the kernel and the mobile electrons or positive charge and negative charge. Okay. So the constant particle is what? Metal atom. Metal atom is nothing but the kernels in a sea of delocalized electron. Kernel means what? The inner electrons along with the nucleus, and the valence electrons are the delocalized electrons. Now nature, they are what? Hard, malleable and ductile. Then melting point is fairly high. Now conductivity. They are good conductors of heat and electricity in solid state. Okay, they conduct electricity in solid state. Now, in case of metallic solids, electrons are responsible for conducting electricity. Electrons are responsible for conducting electricity in case of metallic solids. Now in ionic solids, who were responsible? Ions were responsible for conducting electricity. So that's the difference between metallic solid and ionic solids. In ionic solids, ions were responsible for conducting electricity, and in case of metallic solids, who are responsible? This valence electrons or the mobile electrons are responsible for conducting electricity. Now when you increase the temperature, conductivity of metallic solids decreases. Why the conductivity of metallic solids decreases? When you increase the temperature, what did I tell you? These kernels, they are what? Fixed. Once you increase the temperature, what happens? The kernel starts vibrating. So when it starts vibrating, what happens to the movement of the electrons? The movement of electrons becomes slow. So what will happen to conductivity? Conductivity decreases with increase in temperature in case of metallic solids. Why? Because when you increase the temperature, the kernel starts vibrating, and due to which the movement of electrons becomes slow. So that vibration of kernels in physics, we call it as what? Resistance. What is resistance? The obstacle for the flow of current. So it's nothing but the vibration of the kernels which restricts the movement of electrons. So what happens to the conductivity of metals with increase in temperature? It decreases. Increase in temperature decreases conductivity because movement of electrons becomes slow. So this is the basic difference between ionic solids and metallic solids, which you get questions also. Why conductivity of ionic solids increases with increase in temperature and why conductivity of metallic solids decreases with increase in temperature. In case of ionic solids, the conductivity is due to movement of ions. So when you increase the temperature, the movement of ions in aqueous state and molten state increases. But in case of metallic solids, it's due to what? This mobile electrons, and their movement decreases with increase in temperature. Due to the movement becomes slow. Why? Because the kernel starts vibrating when you increase the temperature. So that are metallic solids. And the next one is molecular solids. Sorry, not molecular solids, covalent solids. In case of covalent solids, the constituent particles are non-metal atoms. Non-metal atoms. And interparticle forces covalent bond, which gives rise to three-dimensional structures. So it's covalent bond. Then nature, they are hard and some are soft, few soft. Then melting point is very high. Why the melting point is very high? Because they have got three-dimensional structures. So naturally the melting point will be what? High. Interparticle forces covalent bond, which gives rise to three-dimensional structures. So the melting point is very high. Examples are what you see: diamond, silicon carbide, quartz, graphite. All these are covalent solids. All this has got what? Diamond has got a three-dimensional structure. Quartz SiO2 also has got a three-dimensional structure. Silicon carbide also has got three-dimensional structure. Graphite also has got what? Three-dimensional structure. So they are very, melting point is very high and they are also what? Hard. Then conductivity. They are insulators. Some are insulators. Mostly all are insulators, we can say, except which one? Except graphite, which conducts electricity. Graphite conducts electricity. So is it clear? So this is known as covalent solids. So in case of covalent solids, the constant particles are non-metal atoms. Interparticle forces covalent bond, which gives rise to three-dimensional structure. They are hard and some are soft. Melting point is very high. Examples are diamond, silicon carbide, quartz, graphite. Then they all are insulators except graphite, which is a good conductor of electricity. So understood? These are the four different types of crystalline solids. First is molecular solid. Second is ionic solid. Third is metallic solid. And the last one is covalent solid. In case of molecular solid, the constant particles is molecules and the interparticle forces either van der Waals dispersion force or hydrogen bond or dipole-dipole interaction. They are soft and their bad conductors are heat and electricity. Then comes ionic solids. In case of ionic solids, the constant particles are cation and anion and the intermolecular force of attraction is electrostatic force of attraction, and they are hard and brittle. They have high melting point and they are good conductors of heat and electricity in aqueous and molten state. Ions are responsible for conducting electricity. Then comes metallic solids. The constant particles are metal atoms or positive charge in a sea of delocalized electrons, and the interparticle force is metallic bond and they are hard, malleable and ductile. They are also good conductors of heat and electricity in solid state, and their conductivity increases with increase in temperature. Why? Because the movement of electrons decreases. Then comes covalent solids. The constituent particles are non-metal atoms, and the interparticle force is covalent bond, which gives rise to three-dimensional structure. They are hard and some are soft. They have very high melting point because they have got what structure? Three-dimensional structures, and they are mostly insulators except graphite, which is a good conductor of heat and electricity. So, the different types of crystalline solids we have already dealt now. Next we will study is how this packing of the particles takes place in a crystalline solid. So, we will study what is crystal lattice or space lattice. Space lattice or crystal lattice. So, it is a total new thing for you. So, listen carefully. Space lattice or crystal lattice. What is crystal? Crystals are made up of what? Constituent particles, that is atoms, molecules or ions. Now, from small class itself, when you think about an atom or a molecule or an ion, we imagine what shape? A spherical shape. So, we represent an atom or molecule or like this with the nucleus inside the center. So, this is how we represent an atom. So, here you see, in order to represent a crystal lattice, we will be just taking the nucleus, and that we will call it as lattice point. So, this lattice point represents what? The constituent particle, which is either atom, molecule or ion. Is it clear? Because the atom, molecule or ion has got what shape? Spherical shape with the nucleus in the center. So, we will be just taking the inner nucleus for representing the atom, molecule or ion, and that will call it as what? Lattice point. And the space occupied by lattice point is called lattice site. The space occupied by lattice point is called as lattice site. So, lattice point is actually what? Atom, molecule or ion. Is it clear? And the space occupied by this lattice point is known as lattice site. Now, what is space lattice? It is the three-dimensional arrangement of constituent particles in space is known as what? Space lattice or crystal lattice. The three-dimensional arrangement of constituent particles, or the lattice point in space is known as what? Space lattice or crystal lattice. I will just write it here and then I will draw it for you. The three-dimensional arrangement of lattice points, in bracket I am writing atoms, molecules or ions in space is called space lattice or crystal lattice. Is it clear? The three-dimensional arrangement of lattice points in space is called space lattice or crystal lattice. So, which gives rise to different shapes also. So, just I am going to make the crystal lattice here. See how I am making it. I am just making the constituent particles, that is the lattice points. It's very simple, you can also try it yourself. See, the next row I am arranging in the space in between the first row. Okay. The third row just I am arranging just below the first row. Very simple it is to make. Now, the fourth row I am just going to arrange it just below the second row. Again, the fifth row just below the third row. Okay. Now I am just going to join it. So you've got a cubical shape. The next. Next. So understood how are you getting a crystal lattice? It is what a three-dimensional arrangement of lattice points in space. That is, the lattice points are arranged and they're joined by what? Lines. So which gives rise to what? Different shapes. So here what shape are you getting? You're getting a crystal lattice with what shape? Cubical shape. So the crystal lattice has got different shapes. You can have different types of crystal lattice according to the way it is arranged. Okay. So this is how arranged. So what can you say here? Different cubes are arranged together and it is giving rise to what? A crystal lattice here. So the three-dimensional arrangement of lattice points in space is called what? Space lattice or crystal lattice. So how are you arranging it? The lattice points are joined by straight lines which gives rise to different shapes to the crystal. Now see here an example I'll give you. When you construct a house, we first arrange what? Bricks. So different bricks are arranged in what? Different directions. The shape and size of the bricks remains what? Same. Same is the case here also. Here it has got cubical shape and all the cubes are of what? Same size only. So what can you say? Here different cubes are arranged in different directions to give you what? Space lattice. Now if you take a single cube from which you have made the space lattice. So its shape is like this. So this has been arranged in different directions. So for study purpose, we can't take the entire crystal. It's very difficult to take the entire crystal for study purpose and to explain all the properties. So we'll take only the part of the crystal lattice. And that part of the crystal lattice which you take for study purpose is known as unit cell. Now here which is the unit cell in this crystal lattice? It's having a cubical shape. What I have drawn here? It represents what? The unit cell. So what is unit cell? A part of the crystal lattice which on repetition gives you what? The entire crystal. So the unit cell will have all the properties of what? The crystal lattice. Is it clear? Because the unit cells are arranged in different directions which gives rise to what? Crystal lattice. So if you take a part of the crystal lattice, that part will have all the properties of what? The crystal lattice, and that is known as what? Unit cell. So unit cell is a part of the crystal lattice which on repetition gives you the entire geometry of what? The crystal lattice. So is it clear? So for study purpose we will be taking only what? The unit cell. We won't be taking what? The crystal lattice, because crystal lattice is what? Very big in size. It has got a three-dimensional arrangement and it's very difficult to take the entire crystal for study purpose. So we'll be taking only a part of the crystal lattice, because the part which you are taking, it will have all the properties of what? The crystal lattice, and that is known as what? Unit cell. Is it clear? So unit cell when arranged in different directions will give you what? The crystal lattice. So how will you define a unit cell? A unit cell, it is the part of the crystal lattice which on repetition gives the entire crystal, So that is known as what? Unit cell. So in the total chapter, we'll be dealing with what? Only the unit cell. We won't be taking the crystal lattice. So is it clear what is crystal lattice? It is the three-dimensional arrangement of lattice points in space is called what? Crystal lattice. So the constituent particles are represented by what? Lattice points, and the space occupied by the lattice points is known as what? Lattice sites. And when this lattice points are joined by straight lines, it gives rise to what? Shape to the crystal. And the part of the crystal lattice which on repetition gives the entire crystal is known as what? Unit cell. So what are the 6 parameters of the unit cell? A unit cell has got 6 parameters. The 6 parameters of the unit cell are here, 3 directions, x, y, z. So these are the 3 edges, A, B and C, and it has got 3 angles, alpha, beta, gamma. Got it? So the 3 edges are, it has got 3 edges, A, B, C, 3 angles, alpha, beta and gamma. So these are the 6 parameters of a unit cell. So the 3 edges may be equal, may not be equal, and the angles also will be equal or may not be equal. It's not necessary. So there are different types of crystals. You have got cubic crystals, you have got rhombic crystals, you have got octahedral crystals. So there are different types of crystals depending upon the arrangement of the constituent particles. So the 6 parameters of a unit cell are the 3 edges A, B, C and the 3 angles alpha, beta and gamma. Is it clear this much? Now types of unit cell. So unit cell is a part of the crystal lattice which on repetition gives the entire geometry of the crystal. So unit cells are classified into 2 categories. Primitive unit cell and centered unit cell. Now what is a primitive unit cell? It's a unit cell which has got constituent particles only at the corners. Such a unit cell is known as primitive unit cell. Now how many corners are there? 8. So it has got constituent particles only at the corners. Such a unit cell is known as what? Primitive unit cell. Unit cell having constituent particles only at corners is known as primitive unit cell. Then comes centered. In case of centered unit cell, apart from the corner, it may have constituent particles at the center of the face. Now this is the center of the face, or at body center. Anywhere apart from the corners, it may have particles at the center of the face or body center or at the center. Such a unit cell is known as what? Centered unit cell. A unit cell having constituent particles at other parts apart from corner is known as what? Centered unit cell. So understood? So unit cells are 2 types, primitive unit cell and centered unit cell. Primitive has got constant particles only at the corners, and centered unit cell will have constituent particles at the corners, and apart from that it may have at the center of the face or body center or at the center. So that will be studying in detail. Okay. Now the centered unit cells are classified into 3 categories. One is body centered cubic unit cell, which is known as BCC. Next is face centered cubic unit cell, FCC, and then end centered unit cell. So these are the 3 types of centered unit cell: body centered cubic unit cell, face centered cubic unit cell, end centered cubic unit cell. So these are the 3 types of centered unit cell. Primitive is only one type. It's known as primitive unit cell or simple cubic unit cell. Simple cubic unit cell. Centered unit cell is 3 types: BCC, FCC and ECC. BCC is body centered cubic unit cell, face centered cubic unit cell, end centered cubic unit cell. Now listen here one thing before going in detail into the different types of unit cell. See, a constituent particle at the corner of a unit cell is shared by 8 unit cell. Okay? A constituent particle at the corner is shared by how many unit cells? 8 unit cells. So what will be the contribution to that particular unit cell? See, if you have a chocolate, if 2 of you are sharing, what will be the contribution towards yourself? It will be half. Same is the case here also. This one constituent particle is shared by how many unit cells? 8 unit cells. So the contribution to that particular unit cell will be how much? 1 by 8. So an atom at the corner is shared by 8 unit cell. So the contribution to that particular unit cell will be how much? 1 by 8. Now, take a matchbox and you keep something inside that. So can that be shared with another matchbox? Is it possible? No. So a constituent particle at the center of the body, that means inside, at the center of the unit cell, cannot be shared by any other unit cell. That belongs to that particular unit cell. That is, if you keep some chocolate or something inside a box and you're keeping another box over it. So that chocolate what you have kept inside the box, will it come in contact with the other box? No. That means it belongs to that particular box only. Same is the case. A constituent particle at the center of the unit cell, center of the body of the unit cell, belongs to that particular unit cell. It is not shared with any other unit cell. So, at the center belongs to that unit cell only. Now, this is the face center. So, a particle at the center of the face is shared by 2 unit cells. So, how many unit cells are sharing an atom at the center of the face? 2 unit cells share. So, what will be the contribution to that particular unit cell? 1 by 2. A constituent particle at the center of the face is shared by 2 unit cells. So, the contribution to that particular unit cell will be how much? 1 by 2. Is it clear? So, a particle at the corner is shared by 8 unit cell. So, the contribution to that unit cell is 1 by 8. Then at the center of the body belongs to that particular unit cell. So, the contribution is how much? 1. Then a particle at the center of the face is shared by 2 unit cells. So, the contribution is 1 by 2. Now, next is edge center. How many edges are there in a cube? There are 12 edges. Now, what will be the contribution towards an edge? Edge center. So, this is the edge center. This becomes the edge center. There are 12 edges. A particle at the edge center is shared by 4 unit cells. 4 unit cells. So, the contribution will be how much? 1 by 4. A particle at the edge center is shared by 4 unit cells. So, the contribution is 1 by 4. So, this is 1. Then number 2, a particle at corner is shared by 8 unit cells. So, the contribution is how much? 1 by 8. A particle at the center of face shared by 2 unit cell. So, contribution is how much? 1 by 2. And a particle at the center of the body is not shared by any other unit cell. So, the contribution is how much? 1. So, this much should be clear because you get numericals from this portion. So, this part should be very clear. A particle at the edge center is shared by 4 unit cells. So, contribution 1 by 4. A particle at the corner is shared by 8 unit cells. The contribution is 1 by 8. A particle at the center of the face is shared by 2 unit cells. So, the contribution is how much? 1 by 2. and at the center of the body is not shared by any other unit cell. So it belongs to that particular unit cell. So the remaining will continue in the next class.